Cool. So I'm going to talk about the statistical view of entropy and then relate that to the third law of thermodynamics. So if you have a whole bunch of dice and you're rolling, say, 2 die. Here's my dice. You got 2 of them. 1, 2, 3, 4, 5. Cool. So 2 dice. Okay, you roll them. And you've seen hopefully that there's 7, 2, and 12. Those are the 2 extremes, are 2 and 12. And then 7 is the one that you most likely get the highest probability of rolling a 7. Because you could get a 7 from 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2. So you have 4 opportunities. Oh, sorry, 1 and a 6, 6 and a 1. So 1, 2, 3, 4, 5, 6 opportunities to get a 7. And so because of that, you're more likely to have that occur. Okay, well, entropy is kind of the same way. Entropy looks at maximizing the distribution of the energy. I'll say that again. Entropy represents maximizing the distribution of the energy. You are not likely to have, based on kinetic molecular theory, where this is the number of particles and this is the kinetic energy of them, it's going to look something like this, to where you have low energy, high energy molecules, and it's a slightly shifted. It's not a nice symmetric Gaussian like you'd have here, but it's slightly shifted. This is kinetic molecular theory. You increase temperature, this shifts over. In fact, this is actually worth going into. Pause. Okay, I'm going to share screen, and I found this wonderful applet that talks about kinetic molecular theory. And it's just important that y'all have this picture in your head when we're talking about entropy. Okay, so here we have, and I'll post this on Moodle so y'all can get to it as well. Here we have at the lower left-hand corner, there's our distribution. This is kinetic molecular theory. Gases are, I'll stop it. And so if I want to say have a very slow molecular count, reset, unstopped. So you can see how each of these states is represented by one of these particular, and I'll slow it down. There we go. Hopefully now my processing speed, you can follow it. And so as you watch these molecules bounce into one another, you're going to have a difference in the distribution down at the bottom. And so if I reduce it down to a molecular count of just a few, now there's just one, there's only one possible state that's occupied. Now, if I increase it, there's a couple more states that are occupied. And if I go to the extreme, now we have a really nice broad distribution. Again, this is kinetic molecular theory. And you can add a heater. So you can add heat energy to the system, such as you're putting more heat energy in, which is going to broaden that distribution. But what's really important is as you add heat energy, you're going to broaden the distribution at the higher energies, and very few are going to occupy the lower energies. That is entropy playing a wonderful game, because entropy, the units of entropy are joules per Kelvin, and that's a very critical point. Okay, I'm going to stop share. So the units of entropy are joules per Kelvin. And entropy, from a statistical point of view, looks at that distribution of energy states. And so when you think about it being disordered, it's really not disorder. It's looking at, you're going from a low number of energy states to a high number of energy states. And the statistical definition of entropy is S is equal to K log W, where this is the number of possible states. Now, the reason we use the logarithm is because we're wanting to add together the fact that you've got this possible state and this state and this state and this state and this state. And when you do that, you're multiplying actually all the possible states together. And the beauty is with logarithms, it becomes addition when you multiply things together. So then you could just add up the states instead of having to multiply them by each other. So S is equal to K log omega. This is like of the famous equations that physics yields for chemists to use. This is one of them. This is one. H psi is equal to E psi, and that's the other. S is K log omega. It was actually so important, Ludwig Boltzmann came up with entropy. It was written on his tombstone. I'm not kidding, it's awesome. Okay, so S equals K log W. What does that mean? This is a number. This is a big number, big number. This makes it a somewhat more manageable number. It's still a big number. What is this? What is K? K is Boltzmann's constant. I'm gonna look it up real quick. I always get it and Planck's constant mixed up in terms of the first few numbers, but the first few numbers don't really matter. It's really the order of magnitude that matters. Okay, so this K is Boltzmann's constant. So Boltzmann's constant says you've got 1.38 times 10 to the minus 23rd joules per Kelvin. So joules per Kelvin. Joules per Kelvin. The units of entropy originate from the Boltzmann's constant, joules per Kelvin. What the hell does that mean? This is a counting number. It could be 2. Let's say it's 2. So K times 2 is K, so it's like, what is that, 1.3 times that, so it's like 2.6 and something, 2.7 times 10 to the minus 23rd joules per Kelvin. Okay, so you're multiplying K by the number of states that you have. That's entropy. But what does that physically mean? So let's dive into what it means to have a joule per Kelvin. So if you have a whole box, just make it this way. So each one of these is a state, okay? There's a state, there's a state, there's a state. Each one of those is 1 Kelvin. Cool. S tells you how many joules you can have for every one of those Kelvin. And it might be that you can have a very high number of joules per that Kelvin, or it could be that you have a very low number of joules per that Kelvin. But if you have, and actually I'm going to write this, ds is equal to greater than or equal to dq of t, where equals is the reversible and greater than is going to be the irreversible process. Heat per temperature. Heat per temperature. The amount of heat energy you can have per unit temperature. Okay. Now, I want to do something kind of fun. Okay, I want to explore joules per Kelvin, and I want to do that through S equals K log W. So if I want to convert this K, or actually I should say entropy, let's convert K to moles. Why not? 1.0, whoops, what was it? 1.03, 1.38 times 10 to the minus 23rd joules per Kelvin. Well, in 1 mole, I have 6.022 times 10 to the 23rd. Get out my handy calculator. 1.38 times 10 to the minus 23rd times 6.022 times 10. You should already know where I'm going with this. Boom. So if you want to know the importance of the gas constant, it originates from the fact that the gas constant is Boltzmann's constant, joules per Kelvin. It's what converts temperature to energy. And entropy tells us what our restrictions are on the amount of energy we can have per unit Kelvin, depending on the system that we're given. It has that chemical character in it. We know that there's a certain amount of energy associated with every degree Kelvin, and that's dictated by the energy, which is dictated by the number of possible states available in our system. Nothing to do with disorder. Slap whoever says it's disorder, and a lot of people do. Pisses me off, but that's fine. It's a functional definition for general discussions. But if you want to get anything meaningful out of your entropy understanding, you need to do the statistical relationship. But we don't really have the ability to do statistical relationships with our gas systems, because how do you calculate what the number of possible states are? That's really hard to do. And it takes what's called statistical mechanics in order to do it. And you need to know a lot about your quantum states. We aren't going that far, but what we can do is at least have an appreciation for where the units come from. I told you you can do most of this class by just a unit analysis and understanding joules per Kelvin. This is crucial. Another fun thing while we're on it, you've all seen this, and we're going to get to delta G is equal to delta H minus T delta S. Gibbs energy is enthalpy minus T delta S. There's your T. RT. R is Boltzmann's constant, K. Okay, you have to multiply the entropy by your temperature to tell you what your actual temperature is. Entropy tells you, so delta S is equal to joules per Kelvin. It's only when you have T delta S, when they're multiplied together, that you have, that's how many kelvins you have, and for every Kelvin, you have that many joules. That's what entropy does for us, is it tells us the dispersal of that energy amongst all of the possible states, which are dictated by kinetic molecular theory, the diagram that I showed, or the animation that I showed you earlier, by what the temperature distribution is. Cool? Bonus. Okay, I think that's, oh, I haven't even told about zeroth law of thermo, or sorry, third law of thermo. My bad. Okay, so for third law, at T equals 0, all thermal motion stops. And in a perfect crystal, all the atoms are in a single state. Okay, this is really, third law is the definition of the absolute zero of temperature. And it says that S equals 0 at K equal, or T equals 0. Okay, and S equals 0 at T equals 0 from this definition, and you might be thinking, well, what is a perfect crystal? I don't understand that. It's all about entropy. If everything in a perfect crystal has only one particular state, one spot that it could be in and nothing else, that means that this is equal to 1. And S is equal to K. And what's the log of 1? 0. So the absolute zero of temperature is defined when entropy is 0. That's how we get to 0 Kelvin. And the only way we can do that is if we make everything really, 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 really cold, which we physically can't do. It's a theoretical limit. It doesn't actually exist. But that requires that everything has to be reduced down to one state, and entropy is itself 0. Go team. So that's third law. So third law, everything stops moving and everything's in one place or in one particular state, S equals 0. First law, or that's third law. Zeroth law, heat moves. First law, heat's conserved, or energy's conserved. Second law, heat's irreversible processes are going to have an increase in entropy. Third law, S equals 0 at T equals 0. Yay! All right, that's all.